Zoom the recording now, so it's now recording everything I say. So if you do need to jump off, or if somebody wants to listen later because they're only just leaving clinic, we can do that. So I'm going to get going in the interests of time. So let me start with a disclaimer. And I've yet to pass part one of the boards. Now, I've never taken it, but I have very little experience in taking the boards. I've also never been an examiner. I've never written questions for the boards. But what I'm going to sort of talk about today is some basic optics stuff, both in geometric optics and ophthalmic optics. I'm going to try and avoid formulae and symbols and instead use words, but just take you through some things. So I think the work that you're doing at the moment for a lot of the subject areas are important. But in terms of optics and some of the other numerical stuff, I think your approach on the day will affect your performance. On a lot of other stuff, if you don't know it, you don't know it. But what I encourage you to do is, think clearly, work carefully, and do check your answers, and don't be limited. I'm assuming they allow you or give you pencils and pens and papers. So just because it's a sort of online exam, you should still feel free to draw a diagram. Okay. So somebody's coming on, and I'm going to mute their video. Hey, Linda, how are you? I'm about to mute you. I just muted you. Give me a thumbs up. There we go. Anyway, so what I encourage you to do is to simplify anything you encounter as far as optics is concerned. If you are given a lens of thickness, or where you think it's a thick lens, figure it out first of all by making it thin. If you're given a toric lens, figure it out as a spherical equivalent or a sphere, but it's also important for some instances to draw a power cross. Remember buzzwords like plano, convex, and meniscus, and it's often much easier to treat a lens as a plano, convex, or concave lens. And when it comes to prisms, treat them as thin. If you have two options of formulae, use the approximate ones, and of course, draw a diagram. Just like anything else that we encounter in terms of patient care, and my teaching assistants just stopped by, so say hi to Calvin. And you've got to ask yourself whether there's you need to use all the information you've been given, or is it just a distractor? And again, draw a diagram. Watch units and signs. We're notorious in optics for using meters, millimeters, and centimeters. So remember, for Prentices Rule, it's centimeters, not millimeters. Pay attention to whether you're being asked about degrees or prism diopters for prisms. And figure out, first of all, whether the surface you're dealing with has converging or diverging properties. And once again, draw a diagram. So I'm going to work on sort of some fairly simple concepts, some straightforward formulae, and I'm going to talk about what I consider to be the three pillars of optics: geometry, trigonometry, and what I call preventive cranioproctology, which of course is making sure you keep your head out of your ass. Okay. So I used to joke when I taught first year optics, the first year course that Dr. Vanderpoel teaches at the moment, that I only ever would teach people two things, but they're the two fundamental things that you need to understand. You need to know what happens to the divergence of light when it hits something, and you also need to know what happens to the divergence of light as it travels upstream or downstream. And I'm going to just pause and remind everybody that I'm going to send you copies of these when we're done. Okay, so unless you want to write something down that isn't on the slide, don't worry about taking notes, because I'm going to go fairly swiftly here. So here's my two favorite formulae, which you know in one form or another. There's two kinds of people in the world. There's the V equals U plus P people, and there's the L prime equals L plus F. And most of you probably learned the second one. Likewise, my other favorite formula is the one for lateral magnification, object vergence over image vergence. You learned it probably as L over L prime. And the reason I like that one rather than alternatives is it works for everything. So those are two fundamental formulae you should know. So the other thing you need to understand is what happens to the vergence of light as it moves through space. We talk about downstream vergence changes. So if we're thinking about converging light, okay, it's going to get more convergy as it moves forward. Likewise, divergent light is going to get less divergy, okay? It's going to get less, it's going to lose its vergence. But in both cases, the vergence of light gets more positive. So as you go from one thing to another thing, or from one lens to another lens, or from a lens to the cornea, the vergence of light will generally get more positive, and that's an important thing to remember. So one of the ramifications of that is vertex distance, and we need to remember that contact lens prescriptions are always more positive than spectacle prescriptions. We can learn the formula, but again, it's better to understand what's going on. So remember, when we have an eye, we have a far point, which is an object location conjugate with the retina. So if we put an object at the far point, we get a clear image on the retina. Now, the key to the kingdom in terms of correcting refractive error is we want to put a spectacle lens in front of the eye, or indeed a contact lens, and we want to make sure that the secondary focal point of that lens is coincident with the far point of the lens. If we do that, remember, for parallel light coming in and hitting that lens, if it's whether it's a minus lens, as is shown here, even though it looks plus, the image for an object in infinity is going to be formed at the secondary focal point. That image then becomes the object for the patient's eye, and if that object is at the far point, they will get an image clearly on the retina, and they'll pay your exorbitant professional fees. So if you look at these distances, these are the three distances that we need to make sure align. So looking at a myope here, you can see that the secondary focal length of the lens is shorter than the far point distance. 1 over the far point distance would be the contact lens prescription. 1 over the secondary focal length of a spectacle lens would be the spectacle prescription. So since the focal length of the myope is shorter, that means the spectacle prescription will be higher or more negative, and it means the contact lens will be more positive. Okay, and you can do the same for a hyperope as well. So the other ramification of light becoming more positive, or its vergence becoming more positive, is that increasing our vertex distance means what hits the eye becomes more positive. So it's an old trick that you sometimes see presbyopes learn, that if they have a high enough prescription, and it doesn't matter whether they're a myope or a hyperope, they'll move their glasses down their nose to read. What they're doing is that they're getting more plus into the system, reducing the accommodative demand. Okay, and this has ramifications for thick lenses as well. Okay, and we'll come to that in just a minute. So when it comes to thick lenses, I think there's way too many formulae to remember. We need to have some idea of where the principal planes are. We need to understand the difference between equivalent power and vertex power. Remember, vertex power is what we measure on the lensometer. Equivalent power is what the important power when we're determining the magnification of a thick lens, like for a low vision aid. And we've got to remember that they have different focal lengths with different names. But as I said before, I would always encourage you to use a thin lens as your first approximation. So if you're asked to calculate the power of anything, calculate the thin lens power first and then go from there. And remember that increasing the thickness of a lens will make both vertex powers more positive. Because just like increasing the vertex distance, just like light going through space, if you add thickness to a lens, the light travels further, the vergence is going to get more positive. Okay, here's question number 1. So mull this one over for a minute. What are the back and front vertex powers of a meniscus lens with an index of 1.6, a rather generous center thickness of 2 centimeters, and front and back surface radii of 6 and 7 centimeters, respectively. So this is an optometry professor's or an optics professor's dream, because you get to write a question devoid of any buzzwords and any signs. So the first thing you need to figure out is, what are the surface powers? Well, the lens form you've been given tells you the sign of each surface. We've got a meniscus lens. It's got a convex or positive front surface. It's got a concave or a back surface. We need to pay attention to the units, but we could draw a simple diagram to remind ourselves, and then we can calculate each of those 2 powers. Front surface power is +10, back surface power is -5, okay? Now, if that were a thin lens, you'd just add those 2 together, so the thin lens power would be +5, okay? Nice and easy. Before you try and use a formula like the one at the bottom to calculate back vertex power, you've got to remember, okay, and before you start putting things into the calculator, you've got to remember it's not going to be too different from 5, and the thickness will make it more positive. So when we go to look at the numbers, there's really only one possible answer here that could be correct. It's a number reasonably close to 5 and a little bit more positive, but of course you could go back and apply those formulae and make sure that you've got the right answer, okay? But remember, if you treat it as a plus lens, as long as it's not ridiculously, if you treat it as a thin lens, as long as it's not ridiculously thick, you're going to get an answer that's fairly close. Anyway, let's go on a little bit, okay? Thick lenses. Remember that there's 2 different focal lengths for each surface. There's a secondary focal length and the back focal length for the back surface of the lens. They're not the same, okay? The primary and secondary focal lengths are measured from the corresponding principal plane. The back and front focal lengths are measured from the surface, okay? So it's those back and front focal lengths that correspond to the vertex power, okay? Because of that, if you've got an asymmetric lens like a meniscus, the front and back focal lengths won't be equal and opposite, but the primary focal lengths, providing you're in air, will be equal and opposite. So if this is an asymmetric lens, we've got all these distances on there, and all I want you to remember, okay, I wouldn't even bother to remember the formula, is to remember what happens to the principal planes when we change the form of the lens. And this is an exercise we used to do in class. So if you've got a biconvex lens, the principal planes are inside the lens, and if it's an equiconvex, then there'll be equal distances from the surface. But when you go to a plano-convex lens, one of the principal planes will be in the plane of the plane of the curved surface. The other one will be somewhere in the lens. And then if you go to meniscus, the principal planes move even forward. The way to think about this and remember it is that principal planes always get sucked towards the more powerful surface. Okay, so if you think about the eye with 2 components, the cornea and the lens, the principal planes are always going to gravitate towards the more powerful surface. Okay, but in a meniscus lens, at least one of the principal planes will be ejected out of the front of the lens. And that's what I said there, and it'll be on the handout. Okay, we just played around with lens form there to see what happens to the principal planes. There are 3 reasons that a lens designer or a vision scientist might change the form of a lens, say from biconvex to meniscus, or change the base curve. Usually we try and keep the surfaces relatively flat because that minimizes the edge thickness. But of course, we choose a base curve frequently that will control peripheral aberrations. And the important aberrations for a spectacle lens are oblique astigmatism and mean error or field curvature. Okay, those are off-axis aberrations. That's what we really care about. And the third reason we might manipulate lens form if we've got a patient with anisoconia is to alter the retinal image size. And the reason that alters the retinal image size is because it's the location of the second principal plane that determines the image size for a given lens. Remember, the back vertex, or the divergence of light leaving the lens, the back vertex power is important in terms of correcting the refractive error. okay, and that will be invariant. We'll need to keep that constant. But as we change the front surface of the lens, we move the second principal plane, and that produces a corresponding change in the image size. So here's some other good formulae that you should remember. I apologize for using P and not F, but these should be familiar. I tend to favor the approximate ones on the right here. The reason being, when it comes to anisoconia and looking at the shape factor, when I look at this formula, it's not intuitive to me what the effect is of increasing the thickness or the front surface power. But the shape factor, that's the magnification produced by the form of the lens, you can rewrite this as 1 plus the thickness divided by n. If you remember first year optics, you'll remember that as the equivalent thickness, times the base curve, the front surface power. Okay, when I look at this formula, I can see very easily that increasing the thickness or increasing the front surface power, steepening the base curve if you like, will increase the magnification. So that formula is more intuitive to me when I'm calculating or thinking about shape factor and power factor. Okay, those are probably good formulae to remember. Okay, you may get asked on mirrors. Mirrors are nice because they behave exactly like a thin lens, except light travels back on itself. So we like to think about light traveling to the right, when you're drawing your initial ray diagrams. But of course, when it's reflected back, just like Beyonce, it goes to the left, okay? Now, the biggest trick that we can pull on you when we're giving you a mirror problem is we can talk about a convex mirror, okay? So when you see the word convex, you think positive, you think converging. But of course, for a mirror, a convex mirror has diverging power. A concave mirror, like the cornea, has, I got that wrong, didn't I? A convex mirror, like the cornea, has diverging power, but a concave mirror, like the good side of a spoon, has converging power, okay? You need to remember and read the question carefully. But nonetheless, the rays coming off the mirror, just like the rays coming out of a lens, if you have diverging rays, then you have a virtual image. Converging rays, you have a real image. And of course, that virtual image becomes the real object for an eye. So here's a question, okay? I'm going to challenge you to answer this question very quickly, okay? So I've got a simple problem. I want you to type in the answers. No shame of getting it wrong, because most of you will probably get this wrong, but there'll be prizes for just attempting. So we've got a corrected one diopter myope. They're looking at a plane mirror. If she's 25 centimeters from the mirror, what's the accommodative demand, okay? Give me a quick answer on that one. Corrected myope, one diopter, 25 centimeters from the mirror. What's the accommodative demand? I think somebody did their homework. Okay, here's the easy mistake to make. You see 25 centimeters, okay, and you think, haha, all right? 25 centimeters, I think 4 diopters. But that's the first mistake you can make here, because remember, when they're looking into a mirror, you got to think about what the object for the eye is and where it is. It's not the mirror, okay? It's the reflected image. That's the object for the eye here. So if they're 25 centimeters from the eye, okay? Sorry, if they're 25 centimeters from the mirror, the image is going to be 25 centimeters behind the mirror, and that becomes the object for the eye. So it's actually 50 centimeters from their eye. Okay, so far so good. The other thing is they're a corrected myope. Okay, you saw -1 diopter, you thought that was important information. Okay, a corrected myope's just like an emmetrope. So in this example, okay, they're just like an emmetrope. They're looking at their reflection. The image is 25 centimeters behind the mirror. So that's going to be 50 centimeters from their eye. Okay, so the right answer here is -2, or B, okay? But full marks to DC and Hannah for taking a swing there, okay? So read the question carefully, okay, and watch for tricks. Now, if they were a 1 diopter myope, what would the answer be there? Well, Hannah and DC would be correct there, and we'll skip to the chase and say it would be 1 diopter. So there's 2 pitfalls here. I love this problem, and lots of previous evil optics professors loved it too, because there's 2 chances to trip you up. Okay, so read the question carefully, draw a diagram. Okay, this next question is the most complicated we're going to do. Okay, it's way too complicated for the exam, but it'll help us review some things. Okay, just related to magnification and accommodation again. Okay, so I've got an uncorrected 1 diopter hyperope. They're looking at their face in a concave mirror with a radius of 100 centimeters. Okay, she's 25 centimeters from the mirror. What's the magnification and what's the accommodative demand? Okay, so there's a number of steps. Each in themselves will be a really good problem. Okay, so what's the power of the mirror? It's concave, just like a makeup mirror. It has magnifying properties if you are standing reasonably close to it. So the power is just -2 divided by the radius. So the lens or the mirror has a power of +2. Okay, so far so good. Where's the image of her face? Well, the object distance, she has a real face. Object distance is minus because she has a real face. And the object vergence is -4. The power of the mirror, well, image vergence is just object vergence plus power, -4 and +2. So we've got -2 coming off the mirror. That's good because, first of all, as we'll see in a minute, that's going to magnify, but we've got diverging light leaving the mirror. That means it's a virtual image produced by the mirror, which can become then a real object for the eye. So we've got minus rays coming off the mirror. That means we've got minus diverging rays hitting the eye, which is what we like. So the image distance is, of course, 50 centimeters behind the mirror, and it's a virtual image, okay? And again, I'll take you through this. I'll give you the handout so you can look at this again. Okay, so here she is in all her glory. So the image is 50 centimeters behind the mirror. And because the image distance is twice the object distance, the magnification's twice the object size. How do we know that? Well, we can use this formula as well. We can take the ratio of the divergences, -4 over -2. So the object is twice the size, it's erect, and it's virtual. Okay, what's the accommodative demand? Well, again, we've got the image 50 centimeters behind the eye. The mirror is 25 centimeters from the eye. So the object is sitting 75 centimeters in front of her. The object vergence is -1.33. That's just the reciprocal of that. So the accommodative demand is +1 minus 1.33. Why +1? Because she's a hyperope. So intuitively, before we get our panties in a bunch over the sign formulae and stuff, if she were an emmetrope, she'd have to accommodate 1 1/3 diopters because she's looking at something 75 centimeters away. Because she's a hyperope, she has to accommodate a little bit more. Okay, so you just add that to 1.33 and you get 2.33. Okay, so we can draw a diagram again to help us remember that. Again, this is way too complex a question. We're just going through some basic principles. We could show off our mad skills even further because we could figure out the angular magnification. And you may not have a formula for this for a mirror, but of course, if we go back to basic principles, you can figure this out. So for angular magnification, remember, you've got to, hey, Annie, how are you? Give us a wave. I'm going to turn your video off, okay? I like looking at you, but there you go. So for angular magnification, you need some sort of reference. So the reference you've been given here is a plane mirror. Okay, so in a plane mirror, they're looking at something 50 centimeters away of the same size. With the concave mirror, they're looking at something twice the size, but 75 centimeters away. So again, you've learned some formulae here. Okay, so that's what I just said in terms of where the image is and how big it is. Okay, so the relative size magnification, which is a very complicated way of saying the lateral magnification, okay, what they're looking at is twice as big as the reference. The relative distance magnification, well, it's further away. So if something's further away, relative distance magnification is going to be less than 1. Here it's 50 over 75. That's just the ratio of the two distances. So when I combine those two, I've got 2 over 1 times 50 over 75. So that's the total angular magnification. So once again, to reiterate, that's probably way too complicated a question than you would be asked on the exam, okay? But we've reviewed some basic concepts. And remember again that you're going to be given a very simple calculator. It won't have trig functions on. So there are certain things you won't be asked to calculate, but you may be tested on whether you understand them. All right, telescopes very quickly. Magnification, remember the sign. Remember Keplerians have negative magnification because the image is inverted. Galilean positive. We need to know the relationship between magnification, length, and the objective and eyepiece power. Okay, those 4 things are interrelated. We need to probably remember about the exit pupil. We need to remember where it is. For a Keplerian telescope, it's outside the scope. Galilean telescope, it's inside the scope. And we need to be able to calculate how big it is. We might have learned about accommodation, but I don't think that's important. So when you're given a telescope that says 4 times 12 on it, you've got to probably remember that the 4 refers to the magnification and that the 12 refers to the objective diameter in millimeters. So very quickly, what's the length of a 5x telescope that has a 10 diopter objective lens? Okay, now even before we start getting into formulae and stuff, a 5x telescope, of course, the eyepiece is going to be 5 times the power of the objective, okay? And you can remember for a Keplerian telescope, both components will be plus. So you can get the 10, you can take the 10 diopters objective power, and you can very quickly come up with 50 for the eyepiece. That's good. And for Keplerian, again, before you get your panties in a bunch over the sign convention, you can basically say, hey, for the Keplerian telescope, the focal lengths add together. So 1 over 50 and 1 over 10 will give us the answer. Okay, if we care about sign conventions, we can do it that way. The magnification is just minus the power of the eyepiece divided by the power of the objective. But to get this right, of course, you've got to remember that for the Keplerian, it's minus 5 and not plus 5. You can then take the reciprocal of the focal lengths and add them together, and you'll end up with 12, which of course is the right answer. Okay. Am I going too quickly, too slow? Somebody type in an answer here while I freshen my whistle. Anybody want to speak? Everybody's sound asleep. I can hear the snoring. Good to go. We can always replay. All right. Am I going to be one of those professors you have to slow down, or one of those you speed up to 2x because it's so boring? All right. Here's another one. A 5 centimeter long 4x Keplerian consists of a 10 millimeter diameter objective and a 5 millimeter eyepiece. The exit pupil is which of these options? Okay. So it's a Keplerian. So before you even start, you can remember that the exit pupil is outside the scope. And you can also do the shortcut, which is to remember that the exit pupil is just the objective diameter divided by the magnification. Specifying or saying that another way, the magnification for a telescope is the diameter of the objective divided by the diameter of the exit pupil. That's a very quick and easy way to determine the magnification of a scope. And the location is given by that formula, but that's all you're being asked here is whether it's inside or out. You can go about this the long way, but I would recommend that you remember the shortcut and just remember the size of the exit pupil is just the objective divided by magnification. And Dr. Yoshinaga or Dr. Bakri told you that. Let's move away from this problem. Okay. You may be asked to combine sphere or cylinders. Okay. Again, the answer may be obvious. It may look like an incredibly horrible, complex problem, but there may be some simplifying that you can do. The thing I always encourage you to remember when you're combining lenses is that the spherical equivalent of the sums is the sum of the spherical equivalents. Okay. You can draw a good diagram. Power crosses have saved our lives many times. Now, I don't think you'll be asked to do vector plots or any of this J0, J45, so I would just sort of forget about that. So look at this problem. We've got two spherocylindrical lenses, two toric lenses that we're combining, and we're being asked what's the resultant power or the power of the resulting lens. Okay, this looks like a horrendous problem until you look closely at the axes and you see they're 90 degrees apart. Okay, so you can either transpose one of them and add them together that way. Okay, if you transpose and the axes are the same, remember, you can just add the sphere, add the sill, and you're good. If you forget to do that, you could, of course, combine them. So you could draw two nice power crosses. So you can probably do this in your sleep by now. But basically, you combine the sphere and the cylinder, put them together, remembering to put the 0 on the axis meridian, not the power meridian, and then you do the same for the other one. You've got two power crosses. You can add those together, and then you can put that back into the regular form. Or you can transpose. Remember, there's some bogus answers here that you can eliminate right away. Okay, so if you realize that the power crosses are or the axes are 90 degrees, you can probably do that very easily. Well, what about this one? Okay, so these two lenses are combined, and now we've got axes or meridians that are now oblique. Okay, you may be able to identify the right answer just by considering the following. The sum of the spherical equivalents is, the spherical equivalent of the sums is the sum of the spherical equivalents. So if you go back to those two lenses, okay, you can figure out the spherical equivalent of the first one. You can figure out the spherical equivalent of the second one, and you can add them together. So the first one's just a JCC, plus 2 minus 4. That's a plano spherical equivalent. The second one's, you add the sphere and half the sill, you get minus 4 1/4. Add those together. All right. Now look at these 4 lenses. Okay. Which of those lenses fits the bill? Okay. What's the spherical equivalent of the first one? Figure that out very quickly. Plus 1, half the sill. So that looks like minus 225. That can't be right. Second one, minus 2.5, half the sill, 175. Minus 425. That could be right. Third one, plus 2 minus 3. What's the spherical equivalent? Plus 2 minus 1.5 plus 050. That can't be right. Last one looks very sophisticated and complex. Okay, minus 140 minus, or add half the sill, which is minus 285. Oh shit, we've got another plausible answer. Okay, now right here, I'd probably just pick the more interesting one and move on. I'm not going to waste any more brain cells on it. If you're adept at vectors and things like that, you could figure it out. But I really don't think they're going to ask you something that's sophisticated. But again, there may be an obvious answer there if you do it. Okay, let's get rid of that. The SAG formula is probably the most powerful formula you learned in the first year because it applies to all these things down the bottom. We use it to calculate the edge thickness of a spectacle lens. It's the basis of the lens clock. So a lens clock is essentially a SAG meter. We use it when we're designing RGP lenses, and we also use it when we calculate the amount of tissue that's going to get removed with a patient having PRK or LASIK. Those are all applications of the SAG formula. What I would encourage you to do is to forget about the exact one and just remember the approximate one. I had lunch with the first year a couple of weeks ago, and I said, I can't remember the exact SAG formula, but I can derive it. I don't waste brain cells on it. I waste brain cells on a lot of other things, but I just remember the approximate one. And again, with the SAG formula, an easy mistake to make is to use the diameter of the lens rather than halving it and using the chord length. Okay, so let's look at this problem here. So we've got a spectacle lens. It's got a back vertex power of -8 and a base curve of +3. It's a relatively thin lens, and we've been asked to calculate the edge thickness, okay? So you might have seen a diagram like this one, where you know that the center thickness plus the sag of the back surface is equal to the sag of the front surface plus the edge thickness, and that applies to both a plus or a minus lens. But that's a waste of your brain power, because it's much easier, okay, rather than going through all this nonsense, which you can go through if you want to practice. It's much easier to just treat it as a plano concave lens and just assume it has a plano front surface. So forget about base curves. It's a -8 lens. You can, if you want to, figure out the radius of the back surface. You can calculate the sag of the back surface. You draw a simple diagram, and you end up with the edge thickness. You've probably, again, from Dr. Yoshinaga, remembered a formula that looks like something at the bottom. The difference in thickness between center and edge is the approximate power times h squared divided by 2 times n minus 1, okay? Whichever you use, whether you go through it step by step or whether you use a one-stop formula like the one at the bottom, it's fine. The thing you've got to remember, of course, is that this is a 50 millimeter spectacle lens, okay? So the important number to consider when you put, whether you use the exact method or the approximate method, you've got to use 25 for H. That's the half chord length rather than using the whole diameter, okay? So you should get that answer. Remember, you may get a question about a lens clock, okay, because it's fairly simple math. It's an example of what happens when you change the refractive index. Remember, a lens clock is likely calibrated for about 1.5. If you put it on a CR39 lens, the true power of that surface is likely to be lower because CR39 has a slightly lower refractive index than crown glass. If you put it on a high index lens, the true power is going to be higher, okay? So you're going to need to remember that formula, I think, that the true power is the power for the clock times n true minus 1 divided by n clock minus 1. Okay, but be careful. Take a look at your answer once you've got it out of the calculator. Take a look at your answer and see and make your mind up whether it makes sense or not. Have you moved the power in the right direction? All right, here's our favorite optics professor or vision science professor. There are formulae that you learn for tilt and wrap. You can forget them, but you do need to probably remember the principles. So what I remember is that when I've got a minus lens, okay, and I tilt it for panto or retro, like Jason's got in this picture, okay, when I tilt it for panto, the important meridian is the vertical meridian, okay? And I can remember that tilting a lens increases the spherical power and it increases the cylinder power in the tilted meridian. So what that's going to do for a minus lens is panto is going to give me more minus sphere power and more with the rule of astigmatism, okay? And if I remember that, I can fill in the rest of this 2x2 sort of square. So if I've got panto for a plus lens, it's going to be the opposite. I'll get more plus and I'm going to get against the rule, okay? And I can take it from the other way for wrap, all right? So, but remember, whether it's wrap or whether it's panto, you get more power, more spherical power in the same as the power of the lens. All right, for aberrations, what's important for the eye, coma and spherical aberration are the important things that we worry about, particularly when we're doing refractive surgery or providing patients with premium IOLs. For a spectacle lens, we worry about the off-axis aberration. Okay, why is that? Well, it's because the eye is a wide aperture system. The diameter of the pupil is quite big compared to the radii of its surfaces. For a spectacle lens, the opposite is true. We've got a big diameter spectacle lens and we've got a very small pupil, but the pupil rotates or the eye rotates and the pupil moves and samples different parts of the lens as we look in different directions, okay? So there, the off-axis aberrations are important, and they are field curvature or mean error and oblique astigmatism. And we also need to remember about chromatic aberration. Okay, so those are things you should have mastery over. Why do we decenter? We decenter lenses to induce prism, and of course we center or decenter relative to the frame to avoid prism. So I would say Prentices Rule is going to rear its ugly head several times on the exam, because it can be applied a number of different ways. So one of the manifestations of Prentices Rule is that when we have a myope, they need to converge. Do they have to converge more, or do they have to converge less? This is incorrect. Okay, a myope must do more when we take them out of spectacles and put them into contact lenses. Okay, so if you have a myope in spectacle lenses, they have to converge less because of the base in prism, and they have to accommodate less for reasons I won't go into, but it has to do what we discussed earlier. So myopes have to converge and accommodate more in spectacles. Sorry, let me rephrase that. Myopes have to accommodate and converge more when they switch to contact lenses, which may be a problem for an early presbyope. Hyperopes, it's the opposite. They do better off in contact lenses. Okay, prisms, what do we remember there? The most difficult thing to remember about a prism is that the light gets bent one way, but the image appears to move the other way. So light gets bent towards the apex, but the image gets moved towards light gets bent towards the base, but the image gets moved or appears to deviate towards the apex. Okay, the only formula I would remember is the thin prism formula. You may have had to, on a midterm or final, resolve prisms into horizontal and vertical components. I doubt you'll be asked that on the exam, but I don't know. It's important, of course, with prisms to remember which eye we're talking about, because base up in one eye has the opposite effect to base up in front of the other eye. And in terms of chromatic dispersion, remember that the blue light gets bent more because the refractive index for blue light is higher than the refractive index for red light. So here's a problem for you. We've got a prism with an apical angle of 20 degrees, and we're being asked to calculate the total deviation when light is incident normally. Now, back in the first year, you probably learned a sort of 3 or 4 step process, and I apologize for the formatting on the slide, where you would have to calculate the deviation at the first surface, then trace the light to the second surface, figure out what happened there, and come up with an answer. Okay, but for this purpose, you really only need to worry about the thin prism formula. Okay, and the thin prism formula is just deviation is n minus 1 times the apical angle. Okay, so in this example, it's 1.5 minus 1 times 20, which gives us 10 degrees. So which is the best answer on this one? A, B, C, or D? Type in your answer. Okay, somebody typed in A. Brave soul. The answer is actually B, because you calculated the deviation in degrees, but the options you were given were in prism diopters. Okay, it's prism diopters because remember, to calculate prism diopters from degrees, you have to multiply by 7/4. So here you'd end up with about 19 prism diopters. So look again when you're dealing with prisms. If they're asking you to calculate something from scratch, do they want the answer in prism diopters or do they want it in degrees? Prentices Rule, getting back to this, it's just the distance times the lens power. The distance can be relative to the optical center. So if you're looking above or below a lens, or the optical center of a lens, or you could move a lens up or down. Important things to remember is that the distance is in centimeters. And for a toric lens with 2 meridians, draw a power cross so you know which meridian is the relevant one. And the other thing, again, I always like to draw a cartoon of a lens. So if I've got a minus lens, if I'm looking above the optical axis, okay, I've got base up prism. But for a minus lens, sorry, for a plus lens, if I'm looking above the optical axis, I'm dealing with base down prism. That's a really important thing, I think, to draw so you don't make a silly mistake. So here's an easy problem to start with. We've got to calculate the image jump for a following patient. We're in a 30mm round bifocal that's set 5mm below the reference point. Okay, so think about that one. And we're just being asked for image jump here. Okay, image jump is caused by the bifocal segment. So the distance power is irrelevant. Where the bifocal is relative to the optical center or the major reference point, it's irrelevant. The only thing that we care about here is the power of the segment and the radius of the segment. Okay, so we ignore the distance Rx when we're calculating jump, and we just apply Prentices Rule to the near add power. And the key thing is the distance from the optical center of the segment to the top of the segment. Okay, it's less for flat tops, it's more for round. So here we have an add power of +2. We have a radius of the bifocal segment of 15mm. We need to convert that into centimeters. Okay, why 15? Because the diameter is 30, the radius is 15. So the distance from the optical center to the top of the segment is what we need. We combine those, we get 3 diopters. Okay, moving swiftly along again. If we are calculating bifocal jump, for the round seg, we use the radius. For D-seg, we have to remember that the top of the segment is always 5mm from the optical center. So we use 5mm, or better still, 0.5 centimeter. And for an executive, in theory, or according to the boards, you've got no jump, but that may or may not be true in practice. But executives you should still think of as a no jump bifocal. All right, here's a more complex problem. We've been asked something different here. A patient is wearing the following. They're wearing a 25mm D-seg with the segment set 6mm below the MRP. We've been asked to calculate the differential vertical. Something weird happened to my sound. You still hear me? Somebody type yes or no. Can you hear me? Who's going to be first to respond? Yes, thanks, Joseph. So we've been asked to calculate the prismatic effect 10mm below the MRP. Okay, so you've got to draw a diagram here just to figure out what's going on. Okay, so for prismatic effect differential between the two lenses, okay, the add is constant and the segment, unless we've done something fancy, is constant. So you ignore the add power here. So for bifocal jump, you ignore the distance power. For figuring out differential prism, you ignore the add power. Okay, you want to draw power cross and you want to figure out the power in the vertical meridian. Okay, then you apply the Prentice to each eye and figure out the difference. Okay, so very quickly, either mentally or physically, draw power cross for these two lenses. Okay, and again, you can ignore the add power. So there's the right lens. Okay, the important power here is the 450 in the vertical meridian. Other eye, -6 is the power in the vertical meridian. Those are the two powers that we're going to use. Okay, we can either apply Prentices Rule to each of them, okay, or we can subtract one from the other and apply Prentices Rule to the difference. Doesn't matter. We're going to end up with 1.5. But again, the key thing is to draw a diagram at the end of all this, and you want to figure out that there's more base down prism in the left eye, okay, because you're looking below the optical center. You're going to have base down prism, so you're going to have more base down in the left eye. So the answer would be 1.5 base down OS, but you could also, another correct answer would be 1.5 base up OD. So I'm going to skip this question. It's on there and you'll see the answers. You may be asked to calculate the total prismatic effect in a bifocal, But I would throw a flag on this question because it really has no clinical relevance. The only clinical relevance for a bifocal is figuring out the difference between the two eyes. Knowing what the absolute prism in one eye is kind of silly. So I'm going to skip through that, but that's you'll see it in the handouts. Okay, I'm going to skip that one too. So I'm going to go on and do a few multiple choice questions here, but if you want to sign off, I do wish you the best of luck. And if there's something that is not in the handouts when I send them around, or when you're watching me at half speed in the on the rebroadcast, then you can ask again. So if you want to sign off, good. But other than that, I'm going to just go through a few multiple choice questions here, just to sort of again point out a few things. So yeah, Hannah says that Darren wants to get one question right and he can't leave. Yeah, okay. So I assume Darren is DC. So nice to have you on, Darren. Okay, so here's a quick question for you. Retinal image of a spectacle corrected hyperope is A, B, C, or D? Which is the right answer? Come on, Darren, give me your best shot. Bring it. Anybody answer? Type in your answer. I'll unmute you all. Okay, full marks to DC. Real and inverted, okay? Our retinal images are always real and they're always inverted. Doesn't matter. The fact we're talking about a spectacle corrected hyperope really doesn't matter. Now, if I change the question up a bit to a myope, what's the right answer here, Darren? Very good. Still C. Okay, our retinal images are always real. Otherwise, we wouldn't be able to see them, and they're inverted. What about this one? So here I'm asking you for the image formed by a spectacle lens of a spectacle correcting myope. Here I'm asking you about the image formed by the lens, okay? So, of course, for a myope, we're going to have an image formed by their spectacle lens, which is a concave lens. It doesn't matter where the object is. It's going to be a image that is virtual and direct, okay? So, full marks to Hannah for getting that one right. Okay. Another question for you. What's the distance from the front surface of a thick lens to the primary focal point called? A, B, C, or D? Okay. It's not the primary or secondary focal length. They're measured, of course, from the relevant principal planes. So here, the distance from the front of a lens to the primary focal point is the front's focal length. So full marks to Joseph for getting that one right. Okay, it's of course, the reciprocal of the front vertex power. Okay, so think about that. Okay, here's a trickier one for you. Ophthalmic optics. We covered this a few minutes ago, so you may know the answer. Spherical aberration is rarely a consideration in the design of spectacle lenses and the choice of base curve because patients adapt to it. Zernike polynomials have saved the world. Coma is much more important. You can't eliminate both. Well, the eye pupil is small relative to the spectacle lens. And DC and Joseph have squawked up. It's, of course, the answer is D. Okay? It's because we're dealing with a small aperture system when we're dealing with spectacle lenses. Okay? It's not true when we're dealing with contact lenses or IOLs. All right, anisoconia. You're designing a pair of lenses for an anisoconia patient. Which of the following will have the least impact on their retinal image size? And again, if you think about what affects the image size, well, if you think about what affects the shape factor, the lens thickness and the base curve affect that. What affects the power factor? The vertex distance affects that. The thing that will have very little change is the pantoscopic tilt. Okay, so A. All right, Chernins ellipses. Okay, very wordy questions here. Okay, what do we need to know about Chernins ellipse? Which of these is false? It indicates that for myopic spectacle prescriptions up to -20, two values of base curves will eliminate oblique astigmatism. Well, it's an ellipse. Okay, it has two solutions, so that could be right. It demonstrates that oblique astigmatism cannot be eliminated in a +10 spectacle prescription. We'll come back to that one. It demonstrates that for some prescriptions between -10 and -20, a concave front surface is required to eliminate oblique astigmatism. That's the false answer. Okay. If you remember Chernins ellipse, the base curve is always positive. It may get very, very flat, but it's always positive. And the final answer, or the final possibility, remember that the size does vary. Okay, so with viewing distance, Chernins ellipses will vary, and with the refractive index, it will vary. Okay, so the thing that's false is C. And remember, one of the other features of Chernins ellipse is that there's no solution for high plus prescriptions. That's why we have to move on to aspherics. That's why even your low hyperopes may benefit from a customized or digital lens. All right, which lens form usually has both principal planes inside the lens? Okay, this is an easy one. Close, Joseph, not quite. It's getting late and I'm talking smack. Okay, remember for a meniscus, one of the principal planes is always outside the lens. For plano convex or plano concave, one of the principal planes is in the curved surface. So it's when you've got a biconcave or a biconvex that you'll have both principal planes inside the lens. Here's a nice one for you. If you've got a virtual object and a concave mirror, what are the characteristics of the image? And the key to this problem is figuring out or writing down the formula for the image vergence for a mirror in terms of the power and the object vergence. And if you write that down and look at the question, you should be able to figure out the answer. So I've got a virtual object, the object vergence is positive. I've got a concave mirror, the power is also positive. So I've got two positives adding together, okay? So I'm going to end up with an image vergence that is even more positive, okay? So positive image vergence, whether it's a mirror or a lens, will give me a real image. It'll give me an image that is smaller, okay? And because both the object vergence and the image vergence are positive, the image will be erect. Okay, so the answer here is B. Okay, so again, we're just applying first principles and putting our thinking caps on. All right, changing the base curve of a -8 lens will not change which of the following? This is one we covered very early on, but should be an obvious answer. Darren, you're going to get this one right for me, bro? Remember, there's three reasons. Way to go, Darren. Okay, there's three reasons that we might change the base curve, or there are three things that change when we change the base curve. When we change the base curve, the edge thickness changes, the oblique astigmatism changes, and the retinal image changes. So the correct answer here is A, the amount of light, which of course will be determined primarily by Fresnel's law. I'd probably remember that formula. Okay, n-1 divided by n plus 1 all squared. 4% for a CR39 lens, a higher percentage for a high index lens. That's why we need coatings. Okay, there's another question for you. Following patient has symptoms that you basically associate with vertical prismatic effect. They got eye strain and occasional diplopia looking through their bifocals. What's the least effective way to manage this patient? And I'm showing my age, and I think actually C, compensated R segments, is no longer in the outline for the boards, but it would be an effective way to manage this. Okay, so as Colin, I think, just chimed in, the thing that won't work is lowering the segment height. Okay, you could prescribe dissimilar segments, which of course will give you differential prism. That would offset the differential prism caused by their anisometropia, or you could do slab off, and slab off is probably the way we would try and manage that in the optical. All right, guys, I'm going to unmute you all so you can talk if you want to. I can see what you're listening to in the background. Any questions? We sort of did a whistle-stop tour there, which you may want to go through again. But hopefully that blew a few cobwebs away, and you felt comfortable at some things, but had some aha moments on some others. Anyone want to say anything?
Thanks, Dean.
Who was that?
This is Darren.
Darren, okay. Thank you, Darren. Thank you for playing. I'll send out maybe I'll just send out the outline to all you 7 people, but I'll send it out to the class later tonight, and you can look at it. And hopefully, if you talk to your colleagues, if you think there's value in watching this, I will if you think there's value, you'll sort of say so to your colleagues. I think we went through it in about an hour, so it won't be a long listen or watch. I'll see if I can get it on lecture capture on the main system, but I may just have to put it on some other medium and you download it. But anyway, good night, everybody. It's about time I had a drink, don't you think? But just so you know, this lecture has been brought to you by Sierra Nevada hazy little thing IPA, and enjoy your evening, stick with it, and I'm pulling for you all. Okay, so I'm going to end the meeting and sign off.